Good morning. This is a webinar on getting reliability from the start, avoiding the warranty trap. We're very pleased to have Fred Schenkelberg, an expert in the field, to be able to talk about the topic. And a little bit about my background. My name is Michael Kira. I've got 30 years of experience in the high-tech product development and commercialization area. I spent about 10 years developing products and then about another 10 years in contract manufacturing. In that span, saw a lot of challenges with the whole process and started Product Realization Group in 2010 to help companies improve. I've done active mentoring at Stanford, StartX, Berkeley Foundry, Lemnos Labs, and have a background in industrial and manufacturing engineering. So seeing a lot of things here in Silicon Valley. And Product Realization Group is a team of hands-on experts that help companies get products from idea to scale. And we've helped many companies in the Valley that are struggling with things like regulatory reliability, commercialization. Think about getting a product from the lab into full scale. So with that, I'm going to turn it over to Fred, and he's going to talk a little bit more deeper dive into the topic of reliability. So Fred, take it from there.
All right, thanks, Mike. And I'm going to leave let's have your mic stay open, and we'll have a bit of a discussion about reliability, try a little different format from a typical lecture stuff. So hopefully that becomes a little more interesting that way. Now, we try in the Valley here, we try to make useful things or gadgets or systems or products, right? And useful would work if it actually shifted there we go. And by making useful things, we often want them to do whatever they're supposed to do, whatever their function is, for some time, right? And I always have this argument with quality folks, quality managers and engineers, is that they say quality is more expansive than reliability. And I say, well, we do everything you do, but we do it over time. And so it's an ongoing debate. Yet, in order to accomplish creating a new system or a function and serving your particular market and creating a solution, is you need to understand your customers, you need to understand the technology, and what we're going to talk about briefly here today is that we also need to understand the reliability, and we'll get some more into that. So, Mike, when you've talked to your clients and the number of companies you work with and startups in particular, what is it that they think reliability is? How would they phrase that? What do they ask about?
Yeah, so good question. I think when I talk to them, the big things that come out are a lot of probably on the fear side. So afraid that product's going to fail in the field, company's going to get a bad reputation, and then that's going to negatively impact the business. Or they make a commitment. Let's say they're in a regulated industry and they have to make a commitment of some duration. The product's going to last a year, 2 years, 3 years, and they're worried that it's not, and then they're going to end up with a big liability. So a lot of it probably, I would say, leans more towards the fear and what's our liability going to be, as well as wanting happy customers. You wanting people to get a product that's going to last to the commitment that the company has made.
Right. Well, is that fear the same as like for engineering requirements or specifications? Do you sense the same, or like are going to do a manufacturer? Do they? Is it the same kind of issues, or I'm not sure what the right word is. Maybe you know what I mean.
Yeah, I think I do. So if the idea is, my experience is engineers are quite comfortable with engineering. That they're creative, they like to design things. I think the fear of reliability is more along the context of scalability, and engineers can play in a lab all day long, but once you get a product into scale, it's no longer playing in the lab. An engineer can't go out and tweak and fix it. It's actually sitting in a customer's hands or a business's hand, and at that point, it really has to work well and be reliable. Not only perform well, but work well over a period of time without an engineer's hands on it. So I think there's a level of, if engineers have control, they're more comfortable. Once it gets out, they're not, and it's like, okay, how's that thing gonna perform once it's out in the field?
Okay, thanks. And one more question is so when do they think reliability happens in their product? I mean, if the engineers are comfortable with the technology in designing something, well, when do they think that reliability happens?
Yeah, so I, I you know, I think a lot of them don't necessarily have deep backgrounds in product reliability, especially people that have come from the software space, kind of migrated from software into hardware. So I think it's understood that this product has to meet some standard. It has to, be reliable for some period of time in the field. I think oftentimes how they get there either isn't known or a little bit is a calculated risk. Meaning, for example, in an IoT product, hey, I'm going to just grab a bunch of off-the-shelf pre-tested modules. Well, we know these are already tested. They've already been through some level of reliability paces. So let's just take a risk and put them together and cross our fingers and hope it works. But yeah, reliability has to be designed in at the very onset of, let's say, product requirement definition, and it has to be maintained through the whole life cycle.
Exactly. Now you're starting to steal some of my thunder here. So. That's all right. So let me just go over real quick what a reliability definition is. And I put this right up front because it's an engineering definition of it. And it's not what our customers often say. Customers just want it to work, right? And they just want it to work over time. They want their solution. And they want all of these functions or the ones that they're interested in. Your product may have 20 functions in it, but they only use 3 of them. They want those 3 to work, right? And so, and I'm sure, Mike, in a lot of your groups, they have requirements documents or engineering specifications and so on that list all the things this widget's supposed to do, right? But a customer is going to call it a failure if one of those functions that they expect to happen doesn't work. So part of the reliability definition is you have to know what you're trying to accomplish, and then what would it be that the customer recognizes as, well, that's not working, right? Now, keep in mind that the function can also be, it has to be a certain weight, and if it's too heavy for your customer or too light for your customer, they may return it or not buy another one or not give you a favorable review or whatever. Technically, anything that costs you money, once it's in the customer's hands, is a failure, right? That I have a very, very broad definition of what a function is. And so that's one part. And we usually, our teams are real good at doing that, right? Let's see if I get my environment is a second part of a reliability definition. And there's 4 parts, actually 5. I'll get to that. But the environment is, where is your product going to be used, right? Is it going to be on a bench inside a laboratory in Silicon Valley? Or is it going to be at the top of a mountain? Or is it going to be underwater? Or is it going to be outdoors portable or whatever? So there's all the weather pieces that go to this. And it's not just temperature and humidity. And I find the teams here in the Bay Area oftentimes forget about humidity because we generally don't have to deal with it unless you have come from Atlanta or the Deep South or someplace like New York City in August. You might not be familiar with the range that weather can have. If you really want to get an experience with weather, is go to Denver, Colorado in the springtime and just hang out for a day. And you're going to wear layers because it might be snowing at 2 o'clock in the afternoon and 70 degrees at 10 o'clock in the morning, and then a beautiful sunset and then a thunderstorm. So it can go all over the map. The other piece of weather is that there's insects and dust and fungus and other things that crash into your product. There's all kinds of ways that the outside stresses can affect your product. And thinking through, which of those stresses are relevant for your product is a start in defining the environment. And another major piece of the environment is the use profile. How does your customer use your product? Is it a 24/7 always on like a server? Or is it a portable device? Or is it something that's only attached to your vehicle and it's just during the commute time, for example, that you expect people to use it? But beyond that is, well, how do you get it from your factory to the customer? And you can even extend this in the environment definitions as, well, how do they dispose of your product? Is it recycled or not? And so on. And all of those pieces, if they don't work to these range of stresses that it sees, if that causes a failure, then you've created a failure. And it's due to the environmental stresses. And so some are easy. We often always think of temperature, yet it's one of hundreds of stresses that your product will see. And so it's think through where and how your product's going to be used. I don't know what. So the last one is really a couplet. It's probability and duration. And whenever I ask people, well, how reliable do you want your product to be? They might say something like, well, we want a very high availability. We just want it to always work and repair times to be very short, which is a probability, right? Or they might say, we want very, very few failures. We don't want to have to pay a lot of warranty expenses. We just want very few failures, like 99 or 5 nines reliable. Well, that's a probability. More commonly, I hear people say, well, we want it to last 5 years. But they don't mention then, well, how many should last 5 years? And that's why I put these both on the same slide. You should always state them together. I want 98% to last 5 years. In 98% successfully operating without failure for 5 years. Now, it's a little different if it's a repairable system, but the same idea is what's the chance it's going to last some period of time? In vast majority of teams I work with have 3 points that they're interested in. And we'll talk about how to come up with these numbers and how they connect to your business in a moment. But when you open a new product and first turn it on and it fails, that's called an out-of-box failure. Now, some industries define it as the first day of ownership or first attempt to turn it on. They might define it as installation period of time, or they might define it as anything that happens in the first month. And some even go out to 3 months, and it all depends on your technology. Warranty, you're probably familiar with warranty and warranty terms. That's when you're financially on the hook to make it right? We'll talk more about warranty in a minute. And then expected use. So if you buy a phone, a cell phone, and it may come with a 1-year warranty, you have the option to buy an extended warranty. I almost always offer you that. But let's say it lasts for a year. Now, if you're like me, I'm going to keep my phone for a couple of years. It's expensive. And the new features on the greatest ones are, really, do I need 3 camera lenses instead of the 2 I already have? So I don't upgrade. I want it to last for 2 years to get my use out of it. So as the many consumer products are built, they're often built to survive in normal use for up to 5 years. Now it's beyond the warranty period, but that failures in that period of time after warranty still cost you money. It might be increased cost of acquiring a customer. It might be bad word of mouth. It might be all kinds of things, but it still costs you money. So as you set out to design, these are the 3 milestones that people often use. Now, I did mention there's a 5th one, and that's all 4 of those change. As soon as your customer gets your product, they're going to want a product that has more functions, right? And they want it to perform longer periods of times with less chance of failure in harsher conditions. So the technical definition is this 4-part piece. Many teams get a couple of these right, but not all of them. And we often forget that when we first set the specifications, it may take us a year or 2 years to get a product out. And in that intervening time, our customers have moved on. They want more. And so, um, Mike, I know you're familiar with this definition. Is do you, when you talk about the fear part, which of these parts do you think the teams you're working with have a good handle on, or which ones are they need to focus on?
Yeah, I mean, from what I've seen with my clients, I think the issue probably that's the biggest unknown would be the period of time. So it's not unusual, and maybe this is a little bit more weighted towards consumer, than others. But I mean, if you look at engineers and put yourself in an innovative company, you're designing a product, you can do a lot of testing and you can play around, but what actually happens in the field, how does it wear? For example, a company had a robot and it was in a home setting, and I think a dog ran into it and knocked it down the stairs. Well, that may not have been something they thought about in the lab. So I think so. Some of it is actually what are the use conditions and other conditions that you haven't thought about, and then the other is how is the unit going to wear over time. We had another consumer product company that had something in the more the external environment, and the plastic ended up eroding fairly quickly. And if you think about it from a customer standpoint, you get a product that really changes form or look in a short period of time. That's really really not very good for the company. So, but those would be probably the two areas I would say are the ones I see the most.
Okay. Yeah, and part of that, especially not thinking through all the ways it can fail, is years ago a friend of mine explained it to me. He says, Fred, every time you come into a room, you tell us about all the ways it's not going to work. He looked at me and goes, it's rather depressing. And I said, yeah, I know that, and it makes it hard to get on an airplane sometimes too. Um, and he said, reliability folks focusing on how way things degrade or change or fade or corrode or wear out or all of the different ways they can fail. And we specialize on that, and that's what we think about. And he says now the engineering teams, the electrical, mechanical, and software engineers, they're thinking about how to get this function to work. They're in success space and you're in failure space. And so I get that. So you walk into a group and you start saying, have you thought about all these risks and all these ways they can fail? And a pretty common response is, well, we're trying to make it work. We're not trying to make it fail. Now, it's part and parcel to the same thing, right? It's one side of the coin versus the other. If it fails, it's not working, and vice versa. So it's just a little shift in perspective is what reliability people tend to bring into, but it doesn't serve anybody by ignoring it. And we'll talk a little bit more about that. I apologize for my slides. My transitions are going partial away, and I don't know what that's about. So anyway, one of the things to keep in mind is that reliability occurs independently, regardless of whether or not you have anybody that even mentions the word reliability in your organization, right? If audience and people watching this webinar have some insight or idea or interest in reliability for whatever reason, yet even if you didn't do that, if you saw this webinar and said, no, I'm not interested in that, your product will still come out of the chute with a reliability. It might not be understood or known until your customers get the product, and then you realize whether it's good or not. But reliability occurs not because you hire a reliability engineer or bring me in as a consultant. I would work with you, and a reliability professional would work with teams to help enable you and your team to make better decisions. What are the risks? What are the elements? What duration? What's the probabilities? What are the things you know and don't know and need to know in order to create a better product? And so the key part is understanding the risk. And Mike, you set me up really well with your answer. One of those questions was, it's understanding not only how does it primarily work, right? And yeah, it would be hard to imagine that a dog would knock your robot down the stairs. Yet it's you got to really stretch and think about all the different ways. If you know that if your robot device topples, that it's bad for it, it's like a fall or a drop, then then anything that causes that to happen, and it might be an earthquake here in the Bay Area, could cause that to happen. Is your product robust enough to survive that? And then it would probably be robust enough to fall over if it just hits the wall or the floor. I guess down the stairs would be an extreme case. But there's also the risk of not knowing how reliable your product is supposed to be, right? If your team is saying, "Oh, we're just going to make it reliable," you're pretty much guaranteeing that each individual will create their own target, and we'll talk about goals here in a moment and how important they are. Yet, to get started with reliability is thinking through, well, take all of those functions that you want built into your product and then put a not sign in front of it to say, well, how will it not do this? How will this plastic not seal or frame this device? How will this tire not hold air? What are the ways that that can happen? And there are specific tools and activities you can use to do that. That makes it a lot easier. Yet it's understanding both what could cause a failure, but also take a catalog of what you know and don't know, or what you're assuming. And a hard part is to sort out what you know you don't know, right? And peel away at those barriers. But you need to understand the risks, and it could include manufacturing risks. I started my career years and years ago as a manufacturing engineer, and I realized very quickly that manufacturing never makes a product more reliable than the design could possibly. We can always make it worse. It's easy to make it worse, but it's impossible to make it better and without a redesign. So I've come to the conclusion it's always the designer's fault when it comes to quality and reliability. Now, I mentioned a number of different tools. FMEA, failure modes and effects analysis, is a wonderful tool. It's like an organized brainstorm to think through, well, how could your product fail? And then a way to rank order and prioritize those kinds of things. Now, reliability engineering tends to have, like almost any engineering discipline, has a ton of acronyms and 3-letter acronyms, 4-letter acronyms, and so on. There's a lot of tools. There's a lot of activities. But keep in mind that these are all tools that can and often should be done, even if you don't have a reliability engineer or quality engineer on staff. Now, folks with this kind of engineering talent tend to be able to facilitate these things and help you with these things, but they're not required, right? You still need to think through what's going to fail and prioritize those. That's an FMEA. If a question comes up, is this vendor's process stable? Am I getting a consistent in-spec product from them? Well, statistical process control is a wonderful tool for that. And then I'll just mention one more. If you're making something new and really cool and inventing things and you don't know how it's going to fail, you just don't know, HALT, Highly Accelerated Life Test, is a wonderful tool for applying stresses to force your product to fail, force it to reveal where the weaknesses are. And then you can use that information to make your product more robust. And so there's a wide range of tools, and this is just a thumbnail sketch of those things. But the key takeaway is that none of these require specific talent and reliability engineering. Sure, if you know some statistics, that'll help. Sure, if you know some failure analysis, that would help. Sure, if you know the mechanics of how things fail, that'll help. But most every engineer has the fundamentals of all of these tools already. And it's just a matter of applying those, not waiting for some outside agent to do it for you. Now, the intent of all this and all these different tools and things that we're doing is because we need to make decisions, right? If we need to know what fails so we can decide whether to use metal instead of plastic, we need to know the environmental conditions we're using are involved in, so we can pick the right materials or the right coatings or the right sealing agents or so on. Is it going to be exposed to moisture? Do we need to make it watertight? Or is it something that's going to be high and dry and we don't have to worry about water ingress? And so on. You need to think through what are those risks to inform your decision making. And then a big part of the reliability tools is to either organize that information and prioritize it, or it's to quantify it. How long before we get failures? What are my targets and so on? Now, vast majority of programs and teams I've ever worked with creating a product prioritize either time to market, cost, or the functions, right? Some are technology led, some are like consumer products are often time to market driven. Yet all of those are measurable on a day-to-day basis, right? Reliability isn't easily measured on a day-to-day basis. It takes a little bit of effort to understand and quantify, is my product reliable enough? Yet at that final design review, a common question is, are we ready to ship? You know, manufacturing's in line, supply chain set up, we have our cost targets, we have enough time to build units and get them on the shelves for the holiday market and so on. We've got all these things sorted out and we're ready to go. Yet somebody is going to ask, well, is it reliable enough? And if that's the first time that question is actually discussed, it's a bit late, right? You might be lucky and it works just fine. So part of this process of reducing your risk and understanding your reliability and building it into your organization is making it a requirement right up front, and then quantifying it and talking about the risks and what can you do to make your product more robust as you go. All right. So one of the questions, remember, Mike, one of the questions we ran into during the panel session we did recently was, well, how much, I think the phrasing of the question was, well, how much reliability, how much investment in reliability do I need to do? And then a follow-on question that I had with a discussion afterwards, well, how do we know how much reliability do we need? How reliable does a product have to be? And there's two questions there. And Mike, so when you're working with these different teams and programs, how do you see teams deal with this? How do they sort this kind of thing out?
Yeah, I think it very much depends on the knowledge of the team and then the industry that they're serving. So, we span medical device, industrial, consumer, and I think the approaches of each of those areas is different. Probably medical being the highest level of scrutiny and process around reliability, industrial next, and then consumer. I think is tends to be much more about speed, and the reliability requirements tend to be less than products that are going to be in the field for a longer period of time. So I think the dynamics that I see really revolve around what is the experience of the team. And I kind of say the teams I like to work with best are the ones that have seen failures already because they know the value of doing reliability early. The ones that have been maybe exclusively software and don't know much about hardware tend to be a little bit more challenging because their thinking is release a lot of things fast and then iterate. And in hardware you really can't do that. I mean, once you have a design locked in, you have to ship it, and then if there is a problem, you can't hit a button and fix it. You actually have to recall it, which is quite expensive and quite painful.
Yeah. And so I agree with you. It'll vary in both the investment part and how reliable your product needs to be. The second question of how reliable does it need to be, and how do you say it? Do I want 98% to last for 5 years, or is 2 years good enough? 98% lasting 2 years it really depends on your industry and what's your competition doing and what's expected from your customers. So if you buy a more expensive product, people tend to want those to last longer. if I buy a 38-cent trinket at the checkout counter and it breaks in a few hours, I probably really wouldn't care, right? I'm not going to do much with that. Yet if it's a $500 item and it broke within the first month, I'm taking it back and I'm going to tell people about it. So it's beyond just the physical cost and the difficulty of repairing it or redesigning it. That certainly plays a factor in it. But it's also what's the impact to your customers' um, appreciation of your product. You know, they because one dissatisfied customer will tell 10 people, one happy customer may tell one. And so you have this, I call it the Yelp phenomena. You have that working against you, and it's probably bet more than a 10-to-1 ratio nowadays. Yet that can be as or more damaging than the cost of a recall and a redesign. And so the way I answered this question during the panel session recently was that you you can't invest or make it reliable enough. You know, there are constraints. Now, I'm speaking as a reliability engineer. Of course, I always want it as reliable as possible. But if you pick that you're going to use a plastic housing on this product, how reliable does it need to be? Well, it needs to be so reliable that the first way it fails is that when it's overheated and the plastic melts, right? Somebody takes a blowtorch to it and melts the plastic. If that's the first way it's likely to fail, that's reliable. Now, there's obviously constraints on cost and all kinds of other things. Yet, if you shoot for a target that makes a robust, reliable product, it has the advantages of you still need to worry about how your customer is going to use their product. But if they decide to take it into a blast furnace or drive it through drive-through, if it's mounted to your vehicle and you're going through high pressure car washes, um, you may not have anticipated those initially, yet because it's robust, because it's durable by design, it's less likely to be damaged by these excursions into unforeseen environments and stresses. And so you don't have those returns for things you didn't think through and you just hope that you got it right. So there's, in my approach, it's invest as much as you can in order to know that you can make good decisions, right? And sometimes it's not a lot of investment. It's some benchtop testing or it's some simulation work and working with your vendors closely and your suppliers. The
Yeah,
quantification.
and Fred, the other thing I would add that I think is a relatively new phenomenon is what I would call the interaction between hardware and software. And I don't know if you can talk to that, but I have seen a lot of issues with clients, especially in the last 5 years, that have called them full stack products. You know, they're hardware, software, cloud,
Mm-hmm.
and the hardware may be fine. You know, you do testing, you put it through, and then the issue isn't in hardware alone, it's in the interaction of hardware, software, and how it all works together. And maybe you could talk a little bit about that as well.
Yeah, it's we used to call it when I worked at Hewlett Packard, we would call that the white space problems. You know, we'd have perfectly good hard drives and we'd have perfectly good power supplies, but if we had vendor A from hard drives and vendor C from uh, uh, power supplies, they wouldn't work together. There was some non-specified phenomena that occurred, some element of it that power supply did not work well with those drives. And those interaction terms are more pronounced the more we rely on software to make our hardware work, and vice versa, to make the products actually function. And so those interaction terms really expand and explode the realm of what we don't know, right? And all those risks that are out there. Years and years ago, when I was a manufacturing engineer, actually, my boss asked me to do some task, and I wrote a quick script to do the data analysis on it, do some of the work with it on a really early version of Excel. And the first thing he did was pull it up on his machine and then hit his keyboard. He hit every key he could hit simultaneously, and it crashed, of course. And he goes, "Well, that's not good enough." Now, there's no way I would have anticipated that he would deliberately try to crash my program. I thought he was going to check the calculations on it. Um, But your customers are going to do this, right? And they're going to use it in all kinds of different ways. And so exploring and being creative and giving it to your customers, taking it home and having your kids play with it, let them do the unexpected to it to see what happens. It's part of chipping away at what you don't know you don't know. And so it's all useful. The hard part is you're exactly right, Mike. It's those interactions. It's you can create perfectly good components and put them all together and have a perfectly horrible product, right? Both functionally and reliability wise.
Hmm.
When you go explore those things, is keep in mind that those interaction terms then basically exponentially grow the areas of risk. And so it's oftentimes the most exciting part is seeing those interactions. And the worst ones are when they're intermittent, because that's usually frustrating to figure out how to solve it.
Yep, absolutely.
Now, one of the things that makes this all work, and we do this with time to market, we do it with what functions we put in a product, we do it with all the other requirements to get to the market, is we connect it to the business, right? Well, it's nothing different with reliability. The first and easiest thing, and I mentioned it earlier, is you're already setting requirements. We want it to be this tall, we want it to be this color, we want it to this little green light to come on when we plug it in, or whatever your requirements are, the set of functions you want it to do. Specify the reliability. I want 98% of these units to operate without failure for 2 years in outdoor North American environments in a portable use, and we expect it to range 2 hours a day of hands-on use, for example. But be specific, 1 or 2 sentences, make it very, very clear. And you want 99.9% to survive the first month. That's the out-of-box piece. And I want 98% to survive 2 years. That's my warranty piece. And 90% to survive 5 years. We want it to be good enough that they come back and buy some more. So by setting it very, very specifically, it helps us to do 2 things. One is it's a requirement. It's visible. We're going to check it. It's in the reviews. It's in the discussions. If we see failures, how does it affect the requirements, especially the reliability piece? If we notice a margin that's just not quite there, well, how much variability are we going to get in manufacturing that causes not only yield losses, but products that go to the field and now won't work long enough, and so on. You got to think through, by setting requirements like you set everything else, so that it's visible and consistent across the entire team. Now, keep in mind that suppliers actually play a pretty big role. That your supply chain can make or break the reliability of your product, right? And just because you pay attention to the part that you're building or designing doesn't mean that your suppliers are doing the due diligence as well. And if you're I hate to say it, but it's not always true. But if you go for the lowest cost supplier, let me just phrase it this way: if you're shopping for suppliers based on price, you will get what you pay for. That's probably the easiest way to say it. Now, there are suppliers that make absolutely phenomenal components and materials at very, very low prices compared to others. But in my experience, if you're in the market just based on price or on delivery and not asking questions about quality, they're going to filter their products. I've seen this done. They'll screen their products and ship the higher quality ones to the people that are willing to pay a little bit more for it. And the more variables and the less constraints on their process and so on, they'll go to you because you're obviously not interested in it. So setting those goals and targets for your system needs to trickle down and be a supply. You need to provide your suppliers that we want this component, but we also want 99.3% of them to last for 2 years under these conditions.
Hey, Fred, one other aspect of this that I think is worth talking about is what I would call designing for the center versus a corner case. And if you can talk a little bit about that, but I've seen a lot of products fail, not because the component was necessarily bad, but it was actually used outside its comfort zone, and it
Oh,
you know
yeah,
it,
yeah,
yeah.
yeah. Yeah, suppliers don't know how you're going to use their product, right? They provide you a data sheet and they say it should work here and here and here, and here's the range of limits and so on. A common technique in mechanical engineering is to do a quick calculation on the stress strength curve. Am I putting enough strength in this, say, flange? Is it engineered to hold enough weight or force compared to the expected loads that the product will see? If those two overlap, on those occasions when your load is higher than your capability of that particular component, it'll shear off, it'll fail. The same in electronics. We call it derating. And if they say, here's a resistor and it's rated to 5 watts, well, if you put 5 watts into it, it won't last very long. It'll do it very, very short amount of time. So if you know you're doing 5 watts dissipation, you need to pick a capacitor that's rated at 10 watts, for example, for its power derating, and so on. The idea is the same as stress strength curves, is you need to help the suppliers are going to help you figure out the features and functions that you need, right? But you should also engage them in, will it work under these conditions? Is this the right solution? Is this the right set of coatings? Is this the right set of requirements or ability to withstand the stresses we see? Now, in general, you can get less expensive parts that your design pushes to the edges of their capability. There's less material, it's robust, it's smaller size, it goes on and on and on. Yet, you're trading off its ability to withstand the variability of the stresses that your product will actually see. Now, any electrical engineer knows that just because that trace is supposed to have 3 volts on it, it may be 2.5 volts, and it sometimes might be 3.5 volts. And every now and then it might be 15 volts, right? Usually for a very short time, you would hope. It's going to vary. And same for mechanical loads. It might be designed for 10 foot-pounds, but it may well be 100 on occasion. So accounting for that variability in the design allows you to design in the margin. And suppliers will often give you a range of options. And I'm thinking electronics here is a capacitor maybe for a 5-volt circuit board will be rated at 10 volts, but they'll have 5-volt ratings, 10-volt ratings, 100-volt ratings, and so on. And they're different price points. And a little bit of thinking helps you to figure out, well, what's the right margin for that? I think it goes back, Mike, to that concept of manufacturing can always make it worse. They add variability, right? That variability of your components and materials combined with the variability of the stresses that you see in the field, that's where those overstress failures happen or rapid deterioration of products happen. And so it's all part of it. And helping your suppliers understand the environment and use conditions and your requirements, including reliability, goes a long way to having that discussion. Am I getting the right parts for what we need it to do?
Yeah, and I
And
would just add one other thing on the supply chain, which is the biggest risk I've seen with components is ones that are provided by, let's say, sole source vendors with an emerging technology, and those tend to be the riskiest. So if you are designing, the more you can design standard components that have gone through lots of testing over a period of time, you tend to lower your risk versus kind of out there first off the shelf design wise from a supplier.
well, it changes the risk, right? And you are taking more risk. But if you account for that and understand it, and you need to do the characterization work, is this the right solution for what we're trying to do? And you need to be heads up about what those intended risks are. But Mike, sometimes that one new invented component is what makes the product's function so compelling, right?
Sure, it gives you a unique differentiator. That's always the trade-off when you're talking about innovation and technology. Yeah.
That's right. Yet,
About
from a reliability point of view, you need to understand that it comes with risks. It probably doesn't have all of the different ways they can fail well vetted out. So we need to go find those out. In working with your supplier, it's to their advantage to understand it too, as they're just coming out with this product. So it's you need to budget for it. You need to line that up and set it up. Now, unfortunately, customers are the final arbiter of your product, right? Now, I actually used this joke at a presentation with the hardware teams at Microsoft. Is if you're Microsoft, you can just ship it, and customers will tell you what's failing, and you don't have to do any testing whatsoever, and they'll tell you, and then you go fix it. Because if you're the only game in town, you have that luxury. They got the joke. The director kind of frowned at me for that one, but we had fun with it. If you want your customers to sort out how bad your design is, then just ship it, right? It will be what it is, right? The reliability exists in your design whether or not you pay attention to it. And it will be independent from your wishful thinking, right? Good engineering, good thinking through it, good analysis helps you understand and quantify what the customers are likely to get. But part of this is also setting the expectations. I had worked with a product, it was a little sports wristband thing, like a Fitbit, but not Fitbit. And they had an advertisement showing people swimming with it. And it really wasn't that watertight. And after a week or so of exposure to a little bit of chlorinated water, it corroded up pretty good on the inside and stopped working. So the marketing teams set the expectation that you can do this with this product. And anybody that washed their hands even or took a shower with this device on, or heavens forbid went swimming, that product failed fairly quickly. And so there's what we set the expectations as matters also. So reliability is not just an engineering endeavor, it's also marketing and understanding where your customers are and what they expect already. Now, once you let a product loose, if you don't go through like a beta program, is let it go to the market, but pay attention. Check back with your customers and find out what's working or not working just to improve your own understanding of how they use the product. But more importantly, what are they considering a failure and what are they overlooking? That helps you prioritize what you need to improve on to make it more reliable in your next iteration. So now, Mike, we named this, avoid the warranty trap, and I'm going to mention that just briefly as we get ready to wrap this up. But do you run into many people that talk about reliability as a warranty issue? When you started off, you talked about, it's kind of the fear of something going wrong and having to do a recall or losing customers. Is that related to warranty and reliability? Are those synonymous, is what you're seeing?
Well, I think it goes back to the level of experience of the client. So clients that have shipped hardware and have seen products returned and understand, what is the liability of warranty issues as well as the brand hit, are quite attuned to the early investment in making sure that those products are not going to fail in the field. I, recently had a client that was very strong in software and they hadn't done a lot of hardware, and they went to CS and found an ODM in China to, kind of leverage for their first product. And lo and behold, when they shipped it, they did get a lot of failures in the field, and it has, unfortunately, in their case, it's actually hit them on their Amazon reviews, and they're trying to make that back because they now understand the importance of and the ownership they have for making sure that product is going to be reliable and is not going to fail in the field. But that's kind of a real life example of if you don't really understand these issues and you kind of take the risk, there is real risk that it's going to come back and hurt you.
Yeah, if they would have gone to another ODM and it all depends on how you phrase those contracts. Can you build this, or can you design and build this for us and we want it by Tuesday and we only want to pay 38 cents? Well, they're going to design and build something that's going to meet those targets, and they will give up things you didn't specify, right? They can make that happen. And so it goes back to you get what you pay for in a large case, but I think it's more you get what you design, what you specify, what you expect, and set the time and budget to make happen.
Yeah, I would say yes, and the end would be um, it really does help to have experts, for example, in supply chain that can go vet because they didn't do a whole lot of vetting on that particular vendor.
Mhm.
And when we actually did help them make a shift because when you dig in, under the covers of the capabilities of that ODM and the quality processes, they really were not at the higher end of the quality spectrum, and that will result in problems in reliability if the manufacturing process and the materials are not very very good
Yeah,
quality going into the product.
yeah, that's very true. Yeah, I've been to Guangdong, and you see a lot of open garage factories that are just along the road, and it's for some products, that's the way it's been made for decades and it works just fine. But if somebody's hand soldering your circuit board together in conditions like that, it's probably not going to work.
Yeah,
It
exactly.
doesn't take a lot
Certainly
of,
going to increase your risk. Yeah.
it's certainly, right? So um, the warranty trap is that if you're in that situation like you just described, Mike, where they shipped it. They didn't think it through real well. They didn't consider the risks that they were facing, and they ended up with bad reviews and products coming back to them and having to deal with that. They're now reactive, right? Another scenario is that you you get some protos, you finally give them over to a chamber and a local lab, and they go do some testing on it, and they say, oh, it caught fire. Is it supposed to do that when it's run for 3 hours? And no, and you have 2 days from the decision, do you launch or not? Now it's all hands on deck. What do we do? You're again reactive. Now, you can build a really good fire department, right? And be really fast at reacting to any issues that come up in the field or in development process and do a lot, but you're still responding to problems. A much better approach right from the start is setting those goals, understanding the risks, and getting ahead of that and being proactive. We're proactive and on so many other parts of running the business, and you need to do the same with reliability. It takes time to design in reliability when you find an issue or find a problem. There was a studies done in the 80s, and it was actually on software development, and it has parallels in hardware, is that for every phase of the development of the program, it costs more to fix stuff, right? If something fails, there's a bug. If you do it early on, it's a quick fix and it costs you, say, $10. If you wait until the next phase and things are getting locked, and you start, like in hardware, you start buying molding equipment, for example. If you need to change that mold, it can be very expensive to fix that. And if it gets to the field, now you have exposed products and changing the design and changing the product at that point. And like in medical products, it may invoke another cycle of approvals and certifications and so on to even bring the improved product to market. So being proactive means that you understand where those failures are, what those risks are, and you design them out of your product and of your supply chain. Reactive is waiting for things to fail and believing that because you haven't seen anything yet that you're good. Well, easiest way to do that is just don't do any testing. Don't turn your product on until you give it to your customer, and then you'll really face reactive responses, right? You'll learn that real quick. We always learn stuff during the development process and shipping a product. The more mature companies actively work to understand all of those risks and all of those decisions, how they impact the final performance of your product, and ahead of time so that they lessen how many times they're surprised. And you still get surprised. Even the best companies I've ever worked with, every now and then somebody figures out a brand new way to use your product inappropriately, and it fails. Yet it's the exception rather than the rule if you get ahead of the game and do it right.
Yeah, and one of the things I've seen companies that has been, definitely effective is what I would call a phased release, to your point, because
Mhm.
especially first product to market, you really don't know what you don't know, and assuming you can figure out everything in the engineering environment, I think is really just not realistic. So having some level of, limited release, getting feedback, and then feeding that back in, and having that time defined in the, call it the commercialization cycle, I think can be quite helpful.
Yeah, exactly. Um, One of the questions I asked you earlier, Mike, was, how much do you invest in this? And I'm certain that many of the teams you work with, especially the startup groups, are pretty strapped for engineering talent and time. It's a balance of how many people you bring in and what do we outsource and all this other stuff and how much funding they have and so on. Over the years, 20 years of doing assessments of reliability programs and organizations, is a, a quick question I always ask the director of engineering is, well, how much of your engineering time, of your talent, is being spent fixing problems on the last design, right? It's gone to market now, it's failing, and we got to fix it. And it's roughly 25%. So if you can afford a quarter of your staff just fixing problems from the last design, that you're right in the ballpark, right? That's pretty average. And it varies, obviously, up and down. Yet it also attests to the fact that if you put a little more effort up front and a little more engineering talent, and probably a little as much as you can afford, is what the way I phrase it, is get that investment up front so that you can whittle down how much of your engineering talent has to be spent fixing things later, right? It's pay me now or pay me later, and pay me later is expensive. So it's one more note there to think of. And the final note on this warranty trap is that if your product goes to market and fails, you're on the hook to pay for returns, to replace it, to fix it, for returns. That in Europe, returns to server products, it's a minimum. Is that if minimum 2 years, it varies, and warranty is just that one element of it. And the key thing here is that warranty, it comes right out of profit. You save money on field failures, you get more profitable, and vice versa. And so it's directly connected to your business. But it's also just a piece of the overall problem. So this is more a rhetorical question, so what can you do about this, right? Well, we outlined a number of things in the presentation of what you can do, and parts of it is robust design, thinking through the risk, and so on. But the intention here is that what you can do is fundamentally four things. Define the reliability. What is it you want your customer's experience to be in the reliability performance? Define it with all four elements and be as clear as you can. Get everybody on the same page. Realize that every decision in your organization is probably going to have a bearing on the final reliability. So if your supply chain is going for the least expensive options every single time, well, think that through. What's that going to mean to our reliability? If you're not taking time to stabilize your manufacturing process, or you're designing it so it's difficult to manufacture, those are decisions that affect reliability. How you market the product affects the reliability expectations, and if those expectations aren't met, then it's a failure, right? And so on. So big part of what we do is enable better decisions, and realizing there's a lot of decisions that occur in organizations that create the reliability outcome. It obviously connects to your business. Make those clear, right? Make those explicit and feed those back into your goals and how you connect to your decisions, and trade them off with time to market and cost and feature sets. And as much as you possibly can, get ahead of the game, right? Be as proactive as you can to understand what your risks are, where the unknowns are, and then work to reduce those risks and reduce those unknowns. And you'll probably do